Morning students, welcome back to online class. I'm Sebastian Galia. Today we are going to study about the new topic that is the states of matter. As we know about the different types of states of matter, that is solid, liquid and gaseous. So here in this chapter we are going to study about the conversion of within the states of matter. So, as you know, as we are going to convert from solid to liquid, it is called melting. So, the temperature measured is a melting point. The state which converts from liquid to gas is boiling point, boiling, and it measured as a boiling point. The state which converts from solid to gaseous is called sublimation, right? So here, these states are interconvertible. Melting point, this is the temperature at which the matter converts from its solid state to the liquid state. It decreases in the presence of impurity. The next one is the boiling point. So this is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. So in the lower class, you might have studied about the atmosphere pressure, which is measured with the instrument called a barometer, right? So it increases in the presence of impurity and with increase in pressure. So the boiling point of water is 100 degrees Celsius. Yes. So if the water is not pure, then might be there is a change in the boiling point. It may be lower, that is 95, 96, or maybe higher, that is 105 or more than that. If it is impure, some other material is present in the water, like salt water, right? So the freezing point, what is the freezing point? Where the liquid gets freezed. So that point is called freezing point. At this temperature, a matter converts from its fluid state into the solid state. So freezing point of a water is 0 degree Celsius. Evaporation. So as you know very well about the evaporation, it is the process of conversion of liquid into vapor at any temperature. So due to evaporation, water droplets appear on the outer surface of a glass containing ice cold water. So that is what called it's an evaporation. It is a reaction between the outer temperature and the inner temperature. So water kept in an earthen pot becomes cool during the summer. Why? Because it reacts on the with the pot. So the third one is desert cooler, cool better on a hot dry day. So in short, what is that given over here? Solid when it react with the liquid, so it's melting, or we can say fusion, right? So when solid liquid turns to solid, that is the water converts to the ice. It's called solidification or the freezing point. Okay. So a liquid turns to gas, it's called vaporization or evaporation. Gas turns to liquid is called condensation. So the name is given condensation. So the law solid to gas and gas to solid is called sublimation in the presence of heat and the cooling. This happens. Take an example of camphor, right? Naphthalene ball, camphor, then odonate, which is using at home. These are the examples of the solid converts to the gas form. Intermolecular forces are the force of attraction or repulsion between the interacting particles. What is the intermolecular force of attraction? So see here, the example is given over here. That is a dipole force. What is a dipole force? When the positive and the negative attracts with each other towards each other is called a force of attraction. So there are two types of van der Waals force of attraction. So what is a van der Waals force of attraction? We have studied in the third chapter. That is, we have studied like this. Van der Waals force of attraction, there is a hydrogen and the hydrogen atom coming closer to each other to form a molecule. For example, helium, take a helium. Towards each other, not hydrogen, helium. Towards each other, it attracts towards each other. But it is not covalent. Why not hydrogen? Because hydrogen is a covalent molecule. And this one is because of the van der Waals force of attraction. The space between these two is more. So the radius, atomic radius of these two atoms is more over here, not over here, right? So why we have given the example over here? Because of its dipole force. So dispersion force means what? Or London force, the interaction which is present between the two non-polar molecules, that is between induced dipole or induced dipole, is called dispersion force. For example, a noble gases. Right now we have given there is a dispersion force. You can say types of one-to-one force of attraction, and here is a dipole. Dipole force means what? Why dipole is given? Because of this positive and the negative force where it attracts towards each other, right? The interaction which is present between the molecules having a permanent dipole between the polar molecule. For example, we can take example of ammonia, NH3 and HCl. So interaction is stronger than the London force and weaker than in the iron-iron interaction. Okay, stronger in the London force because the attraction is more, and here weaker in the iron because only the positive and the negative particles are interacting over here, right? Suppose we have two atoms, that is atom A and atom B, in the close vicinity of each other. See here in the figure. So it may so happen that momentarily electronic charge distribution in one of the atoms, says that is A, becomes unsymmetrical. That is, a charge cloud is more on the one side. So the charge particle, see the charge particle is goes on the one side, is the cloud of this one. So this results in the development of an instantaneous dipole of an atom A. So the atom A is getting dipole. So this is a positive charge. So the positive charge is written like this, and the part is negative. So from the figure, we should understand, okay, where is the diagram? If the positive charge is over here, so how the way to write the charge like this, and you show the part like this. So this is a positive charge over here, right? See, it is written like this. So from the figure, we can understand, okay, where the positive, obviously, where the positive charge is there, the other part is a negative one, right? So atom A with the instantaneous dipole, more electron density on the right side, hand side, and B induced with the dipole over here. And see over here, there are different parts of the electrons. How it is in the center, there is a symmetrical distribution of the electron charge cloud, and here more on the right side and more on the left side. So here the temporary dipole of an atom A and the B attract with each other. When it will attract, when there is a negative, so it will attract with each other. Similarly, temporary dipole are induced in molecules also. So this force of attraction was first proposed by the German physicist, that is Fritz London. And for this reason, force of attraction between the two temporary things are given over here. The next one, see here. The second one is a dipole-induced dipole force. Now, what is dipole-induced dipole force? That is a force of attraction between the polar molecule having a permanent dipole and a molecule lacking permanent dipole. So see here, this is the polar one. Why polar one? Because it's having a negative and the positive together, right? So this was the non-polar. So when these two react with each other, then what will form here? One is a permanent dipole, that is a polar one, and induced dipole, that is a non-polar. So what is the difference polar and the non-polar over here? See here, here it's a permanent dipole. Attraction pin there is there, and here is the induced dipole. No attraction is over there. Okay. The next one is the gaseous state. This is the simplest state of a matter, which is the characteristics of the states of matter are in gaseous, the intermolecular forces are weaker. For this, we are studying from the lower class only, right? Intermolecular forces are weaker because of the less molecules, right? Gases are highly compressible. Gases exert pressure equally in all directions. Gases have a much lower density than the solid and the liquids. The volume and the shape of the gas are not fixed over here. As you know, it is very light in weight. It goes here and there. So there is no shape of gases is there, and no volume also. Gases mix evenly and complete in all the proportion without any mechanical aid. So these are all the properties of the gaseous state. Now, the measurable properties of a gas is mass. It is expressed in the gram or kilogram. Volume. It is expressed in the liter, milliliter, cubic centimeter, cubic meter, and cubic decimeter. That is 1 liter equals to 1000 ml. That is equals to 1000 cubic centimeter, and that is equals to 1 dm cube. Right. So 1 meter cube equals to what? 10 raised to 3 dm cube. That is equal to 10 raised to 6 cubic centimeter, and 10 raised to 6 ml. That is equals to 10 raised to 3 liter. So this conversion you have to understand. Now about the pressure. So gas pressure is measured with the manometer and the atmosphere pressure is measured by the barometer. Right now we have discussed that is gas pressure is measured with the manometer and the atmosphere pressure is measured with the barometer. That is 1 atmosphere pressure, that is equal to 76 em of mercury, or that is equal to 760 mm of mercury, that is equal to 760 torr. These are all conversion you have to remember. So basically 1 bar equal to 10 raised to 5 Pascal. EA is what? Pascal. Okay. So 1 atmosphere equals to 101.325 kilopascal, that is equal to 101325 Pascal, that is equal to this much of nanometer per meter square, that is equal to this much of bar. So basically we can write 1 bar equal to 10 raised to 5 Pascal. Okay. Temperature, it is measured in the Celsius scale or in a Kelvin scale. SI unit of a temperature is Kelvin. That is, Kelvin equals to temperature plus 273. So you know very well. So what is the standard temperature and the pressure? Standard temperature, STP or NTP. Can write NTP, normal temperature pressure, or standard temperature pressure, which means 273.15 Kelvin. That is 0 degree Celsius temperature, and the bar pressure, that is 10 to 5 Pascal. At standard temperature and pressure, molar molecules volume of an ideal gas is 22.71098 liter mole per inverse. Now about the gas law. There are 4 gas laws we are going to study about over here. That is Boyles Law, Charles Law, Lizak's Law, that is a Gay-Lizak's Law, which is there in the textbook, and the next one is Avogadro Law. So at the last, we are going to get the Dalton's Law of partial pressure. Right? Let's start about the Boyles Law. So here, the volume of a gas of given mass of a gas is inversely proportional to the pressure at a constant temperature. That is, volume is inversely proportional to the pressure. So Vp equals to constant. How to write over this one here? See, volume is inversely proportional to the pressure. So V equals to K upon P. If we are removing the proportionality and then we will write equal and then K for constant. So that is Vp equals to K. So K is a constant and its volume value depends on the mass, temperature, and the nature of the gas. So PV or Vp, we can write it so as it is constant. So P1 V1 equals to P2 V2. Right? So as the volume increases, pressure decreases over here, right? And as the volume decreases, the pressure increases, right? So the isotherm graph of the volume versus the pressure, which is given over here, see here. So it starts from over here, and the volume is decreases. As volume decreases, pressure will increase. Okay. So P raised to P versus 1 by V volume, and here PV raised to temperature over here. Now, the next one is a question about the numericals. A balloon is filled with the hydrogen at a room temperature. It will burst if the pressure exceeds 0.2 bar. If at 1 bar pressure, the gas occupies 2.27 liter volume, up to what volume the balloon will expand? So when we are blowing the balloon, till what pressure it expands? When we have to stop, right? So the question is about that. So we are using the Boyles law, that is equals to P1 V1 equals to P2 V2. So P1 is 1 bar, it is given over here. Volume is 2.27 liter. P2 is given 0.2 bar. If the pressure increase, then what the volume will be? So apply the value over here. P1 V1 upon P2. 1 into 2.27 upon 0.22 bar. Don't forget to write the units, right? So when you calculate using the calculator, you will get 11.35. Just check it out. And the volume will be returned. So since the balloon bursts at 0.2 bar pressure, the volume of the balloon should be less than 11.35. So this is the calculation, right? This is the theoretical calculation. Okay. Just varies with the material of the balloon also, right? Charles law. The next one is the Charles law. At a constant pressure, always remember, for constant pressure, the volume of the gas given mass of a gas is directly proportional to the temperature. That is, V is directly proportional to the temperature. Inversely means V is inversely proportional to 1 by P in the Boyles law. Now here the pressure is constant over here. So V by T is a constant. So let V1 be the volume of a gas at temperature T1. So the pressure remains constant. So V1 upon T1 equals to V2 upon T2. This is what? This is the formula for the Charles law. That is V1 upon T1, that is equal to V2 upon T2. Alright? The next one is what? The third one is the Gaseous law. Here, what is constant? Obviously, the volume is constant over here. Here also, pressure is directly proportional to the temperature. As the pressure increases, temperature is also increases. As the pressure decreases, temperature decreases. Fine. So P by T equals to constant over here. So see here, V1 is less than V2 is less than V3 and V4 is the mole. So as the volume increases, the temperature also increases. So the relation can be derived from the Boyles law and the Charles law that pressure versus temperature Kelvin at a constant molar volume just given over here. So each line of the graph is called isopore. What is called isopore? Fine. The next one is the last one is the Avogadro's law. So it is stated that the equal volume of all the gases under the same condition of temperature and pressure contains equal number of molecules. Mathematically, we can write over here V is directly proportional to the number of mole of the gas. So V equals to K constant N. So the number of mole, as you know, N equals to mass upon molar mass. So mass of the gas upon molar mass. So substitute the value of N over here in this equation. So V equals to K upon K M upon capital N. There is a molar mass. So what is a molar mass over here? K M by V. So we can write M by V is what? Mass upon volume is what? Density. So we can write M equals to KV. Okay, understood? If you don't understood, repeat the video. Okay, and then see. So what is the ideal gas equation? When we are adding all the Boyles law, Charles law, and the Avogadro law, we are getting one universal gas constant equations. Ideal gas constant equation, that is P is inversely proportional 1 by P at T and N constant. V is directly proportional to temperature at P and N constant. V is directly proportional to the N at P and T constant. Right? Written all the formulas together. Now add all the things. What is P? Is directly proportional to N and T upon T. Okay. So V is directly proportional to N upon NT upon T. So that take a proportional and write R as a constant R and T upon P. So take P over there. So what we will write? PV equals to, we will write nRT. Got it? So here K is not a constant over here. This is R is known as a universal gas constant. Okay. So PV equals to nRT. This is the main formula for the ideal gas equations. See here how it forms. The density and the molar mass of the gaseous constant over here is ideal gas. N upon V equals to P by RT. This is the ideal gas equation we are rearranging in this format. So N by V equals to P by RT. So N is what? Mass upon molar mass. Substitute the value over here in the M upon capital M V, that is equal to P RT. So you have to remember what is this written. If you don't understand, just write PV equals to nRT. So from the ideal gas only N upon V is taken and RT is over here. Okay, there is no any confusion over here. Okay, so by replacing N over here and M upon capital M, just substitute over here. As we know, M upon V is density. So D is written over here. So D by capital M equals to P by RT. So what is capital M? Capital M equals to DRT upon P. So what is this one? M, that is a molar mass. What is that? That is a molar mass. You have to remember the numerical value of the R. That is R equals to 0.082 liter at atmosphere, mole inverse, Kelvin inverse. R equals to 0.083 liter bar, mole inverse, Kelvin inverse. R equals to 8.314 joule, K inverse, mole inverse in a different way. So these are all the value of the gas constant. You have to remember it. Maybe used in any Why? Because of the different units. We have to focus on the units, right? So what is ideal gas? The gas which obeys the equation, that is PV equals to nRT at a temperature. The pressure ranges strictly is known as an ideal gas. Real gas is what? Since none of the gas present in a universe strictly obeys the equation, that is PV equals to nRT at a low pressure and the high temperature. So see the numerical is given over here. Try to understand the numericals right now. As you can see here, the temperature is given, the pressure is given over here. Just substitute the value over here. First of all, what is given over here? Pressure is 768 mm mercury, volume is 600 ml, temperature is 25. Always remember that you have to convert in the Kelvin. So volume is 640. How 640 ml comes? Just tell you over here. T2 is given over here, all right. So T2 is 10 plus 273 Kelvin. We have to convert into Kelvin. So just combine all the formulas, that is PV upon T equals to P2 upon T. So what we required the pressure at a high. So P2 equals to P1 V1 up T1 P2 upon T1 and V2. So if you use the formula, always try to write with the unit. So at last we are getting 676.6 million mm mercury. Okay, unit, don't forget it. All right. So the last one is what? Is Dalton's law of partial pressure. So it's a Dalton's law of partial pressure. So at constant temperature, the total pressure exerted by the mixture of a non-reacting gas is the sum of partial pressure of the different gases at a pressure in the mixture. So P equals to P1 plus P2 plus P3, and it goes on, right? So at a partial pressure of a gas, that is equals to mole fraction of a gas at a total pressure. So PV equals to N1 plus N2 plus N3, that is RT. R is what? Gas constant, T is a temperature. So this is the equation for the gas state of the gaseous mixture. That's PV equals to N1 plus N2 plus N3 and RT. PV equals to nRT. So we know, right, very well, right? So see here the numericals given in the textbook. All the numericals are very, very important over here. A neon dioxygen mixture. The neon dioxygen mixture contains 70.6 gram of dioxygen and 167.5 gram of neon. So if the pressure of the mixture of the gas in the cylinder is 25 bar, what is the partial pressure of the dioxygen and the neon in the mixture? So the number of mole of the dioxygen is what? 70.6 upon 32. Find the mole of the dioxygen as well as the neon. Okay, so we have to find the mole fraction. In the previous questions, we know that is Na. If we are finding Na, so Na upon Na plus Nb. So this is the formula for finding the mole fractions. So that is 2.21 upon 2.21 plus 8.375. So we are getting the mole fraction of dioxygen over here. And the neon is what? That is Nb upon Na plus Nb, right? This is a mole fraction formula. Always remember, substitute the value. We are getting it 0.79. So what is this mole fraction of the dioxygen and the neon? So the mole fraction of the neon is what? 1 minus 0.29. We are getting directly also this one. So this is two methods of finding the mole fraction of the neon. So the partial pressure of the gas, that is equal to mole fraction, total pressure. So partial pressure of the oxygen is what? 0.21 into total pressure, that is 25. So if we will calculate that one, we are getting is 5.25 bar. So partial pressure for the pressure of the neon is what? 0.79 into 25. 25 is the given pressure bar over here. So the partial pressure we are multiplying, we are getting answer bar. Okay, understood? Hope you understood the topic very well. Thank you. Read and solve the numericals. Have a nice day. Bye-bye.